G'day everyone. Alright, we'll make a start for today. The first couple of minutes, Marion from Accessibility Services is going to speak to you about what services they actually offer. Some of you might find that quite useful, some of you might be across it already, but nonetheless. And then we'll get into design. So I'll hand over to Marion.
Hi guys, I'm Marion, one of the two student advisors in Accessibility Services. And there's another staff member who also know T's, who you will run into along the way if you have any contact with us at all. If you're a JCU student, stick your hand in the air now. The rest of you are just here because you like group gatherings, is that right? Leave it up there unless you can guarantee you will not get hit by a truck this semester, get a mosquito-borne disease, break both wrists while playing extreme frisbee and study back, which has been done. Please don't do it, but it's been done. You or anyone you know doesn't have a learning disability, mental health problem, chronic health condition, or plans to acquire one, and you can guarantee that. If your hand is still up, then good on you, you're paying attention, because it should be most of you. Because what we've got is actually relevant to you and to heaps of people that you will know, so do pay attention for the next couple of minutes. There's lots of students who will do first year uni and subsequent years of uni much harder than they need to because they're managing all sorts of extra stuff about their health as well. We are not here to say you're not capable. We're not here to say that you get a free ride either with us. But the idea is from Accessibility Services you can access all sorts of assistance with the ways you liaise with your lectures, the way you manage your studies, the way you've got access to materials, the way you can turn a slide that's multicoloured and a bit busy into something that's more readable if you're already having difficulties reading that sort of stuff because of the way it's formatted. The way you sit exams so that the conditions are a bit more civilised, no free ride, just a bit more civilised, and they're not getting in the road and making life harder for you so that you can get on with doing the stuff that you've come here to do, which is learn all about EG1000 and be able to show all the work that you've done during the semester at the end of it without being further disadvantaged. You access that sort of stuff by coming and having a chat to us and seeing if it's relevant. You can find us in the first floor of the library. The student wellbeing at jcu.edu.au email address will let you contact our central desk there and be able to book you in for appointments. And that's the start of the process where we're working with you while you work out how you can be functioning at uni so much more easily, more effectively, and building up those skills that you're going to take into the marketplace and say, pick me, give me all your money, I'm worth the job, not just because I managed to get through uni while managing things about my health, but because of it. Because sometimes our students have thought about how they work more than other students and they've actually got one up on the other people in the job queue because they've been able to work out strategies for being able to be successful and be highly employable. If you've got any questions at all, the way to get them solved is to come and have a chat with us. We're really happy to talk with you even if you're not looking to register. It's totally confidential. We're not connected to anybody who does any of the marking for any of your subjects, so it means that you can have somewhere to go and sort out how you're going to work, but we can assist you with the communication that you'll use down the track. Yep, you're in the right place. Come on, sit down. We'd like to see you, and it makes lots of sense to come and see us early rather than late. There's plenty of crisis management happens on campus and plenty of the staff get used to doing it, but it works so much better if you come down and see us much earlier along in the semester. Thanks a lot, we hope to see you.
Alright guys, so as you can see, there are a lot of different things set up in the university, mechanisms set up in the university to help you guys. Other things related to if you get sick around exam time or if you've had a hard time during semester and all of that kind of stuff, if you toil along alone, you might actually miss a lot of the really helpful things that the university has in place to help you out. So talk to us, talk to people like the Accessibility Services, and they can actually structure various things like when you sit your exam and how you sit your exam and all of that kind of stuff. So don't just, get hurt and just think you have to suck it up or whatever. There's lots of different things that we're here to try and help you guys get through in all circumstances, okay? All right, so let me just pull up my stuff. There we go, and we'll get started for the day. Okay, so has anyone put into practice any of the study skills that I put on the lecture last week? Anyone had a chance to use any of that yet? Some of you? Excellent. I thought I'd just clarify one little thing that occurred to me after I walked out of the lecture in regards to what classifies as a solution. So you know how I was really banging on about don't look at the solution, try and use your mind? In some circumstances, you'll have a problem to solve that will have a solution, and so don't look at that necessarily when you're studying. And studying is different to a tutorial as well. But you might also have a problem that you're trying to solve that you have another one written out that's very similar. So an example problem in your lecture notes or a textbook or something like that. That is a similar sort of a thing to answer in the back of a book, okay? So don't just assume that because it's a different problem doing the same thing that it's not classifying as what I was talking about. So when you're in a tutorial, chances are you're going to need that problem to work through the problem that you've been given in the tutorial, all right? You're not expected just to understand how to solve a problem, all right? So in the tutorial, chances are you'll probably have your example problem on the left and you'll try and solve the problem on your pad or whatever you've been given. Now, when you go home to study, or you're studying in a week's time or 2 weeks' time, that isn't sufficient for studying that content then, all right? You've done it once, you might have done it a couple of times, but once you're actually trying to study it and commit it to memory, just looking at the example problem and solving another problem isn't any more sufficient, okay? Because you're just doing the same thing. You're learning the same thing you learned in the tutorial. You're just going through the motions. What you want to do is start trying problems without the work solution beside you, be it the actual solution or an example solution. And that might be the first time you do it, you might just try to do the first half and then look at the work, sort of the process, and then do a little bit more until you're starting to do problems all by yourself, all right? So you need to get your mind to a point where you can do it without looking at the work solution or the actual solution. Okay, does that just clarify that a little bit for everyone? You're trying to get to a point where you're able to do it by yourself. And any type of solution, be it the exact solution or a similar one, will decrease the amount you're learning from the experience. You need to stretch your mind whilst you're doing that. Writing out flowcharts and things is very useful because if you have a work solution example, rather than look at that, write out a flowchart with the equations and then reference that, rather than the actual solution itself. That, just making that and then referencing that starts to move things in your mind that allow you to function really well, particularly in maths and physics types problems. Okay, so that's just a follow-up on the last lecture. If you haven't put any of those into practice with maths and physics, you've got lots of opportunity to study already. So I suggest you start thinking about those type of ideas that I was talking about in the last lecture. All right, but around our learning outcomes, that was number 6. So obviously we're starting to talk to you about university life and what's helpful. And we also talked last week about the grand challenges, which is number 1, and particularly while also recognising the broader function of engineering in society. All right, you start to get an understanding of where engineering sits in society and the big problems that we have to solve. All right. This week and next week, and largely for a lot of this semester, we're going to be talking about systematic approaches to engineering design, and this lecture is the introduction to that. I've got a few slides, and then there's an example, and then in tomorrow's tutorial, you'll do a bigger example on the problem specification that I'm going to get you to do today, based on your actual bridge project. All right, so tomorrow you will get the outline and everything for the bridge project that you'll be working on for the first part of the semester. And you're going to practice the first step of that in today's lecture. But before we get into that, what is engineering design? Do you guys have an answer to that? Anyone? Yeah, so look at a problem and design some sort of solution. Anyone else got anything else? You guys are in engineering, yeah? Sorry? Structure planning? So planning around what? Planning around building a structure or the structure of design or? Yeah, okay. Anyone else? Yeah, so when you're designing, you can generate multiple solutions. Design's pretty open-ended, and I'll talk about that. But fundamentally, design can be, there's many definitions to design. So it can be everything from minor improvements to a particular product or something really out there and designing something brand new from scratch that's never been done before, and everything in between. Okay, there's a couple of examples on that slide. So you've got the Joint Strike Fighter or whatever it's called, top left. Obviously thousands of engineers working on that, and basically every type of engineer, I'm not sure how many civils, but pretty much every other type of engineer will be working on that. If you think of all the electronic systems and avionics and then fuel systems and then, you know, obviously all the mechanical systems, the aerodynamics, everything like that, you've got thousands of engineers all working on that. You got the building we talked about last week, 820 whatever it is metres tall, all of those different systems. And so these are the really big scale type, design from scratch, something really out there kind of things. But there's lots of examples where design takes a smaller component or a smaller improvement or something, and you still put in the same design process if it's a tiny improvement or a brand new product. All right, let's just kind of distinguish engineering design from maths and science. So on the left there, we've got a resistor. You guys, anyone done things like resistance, electricity, voltage, so forth in school or just playing around with it? Yeah, most of you are pretty familiar with this idea. So we got our resistor, and the equation P equals I squared R is science. Somewhere along the line, some scientists did a bunch of experiments on some wire and worked out the relationship between power dissipated and the current and the resistance and so forth. Okay? The actual equation itself and defining that phenomena, that physics, is the science. Science and maths and so forth. Analysis is using that equation. Okay, so in the analysis column, we've got P equals I squared R equals 500. All right, and that's because we've got a resistance of 20 and we've got an ampage of 5. We can calculate what power is dissipated for that particular circumstance. That's analysis. And engineers use analysis in a lot of different areas. On the right-hand side, we've got some resistance, some amount of amps, but we want a particular power dissipation. How many different options have I got for R and I on the right-hand side? Infinite? Anyone want to raise me on infinite? What type of resistances do I get resistors from if I buy them off the shelf? Do they come in every single 0.698754321? No. So they come in pretty standard things. Now, if you've got a really custom job, maybe you design your own resistance that's 0.5496, whatever it is. But for the most part, you go to a catalogue and you have 1 ohm, 2 ohm, 3 ohm, 4 ohm, whatever. All right, so that starts to restrict the problem. What about currents? Anything restricting current? Maybe power sources, depending on what the sort of problem is. But for the most part, we've got infinite solutions over on the right there. There's technically no right solution. There's many possible solutions, and there's trade-offs. And there's these things like standardised resistors and standardised power sources and things that start to refine the possible solutions. But for the most part, design is open-ended. And you need to use the analysis, and you need to understand the science, but you also need to start thinking about the broader picture and the product and how we actually think about it. All right, that's a really simple example of design, but that's what we're going to start talking about. And the real problem with design, and what is challenging for people to get their heads around, certainly in the first year, in the first instance, is the fact that it's open-ended. There is no right solution. There is just a number of reasonably good solutions, and you need to work out which one is the best. And normally working out which one is the best is how much is it going to cost and how easy is it to implement and how well does it solve this problem without ruining this problem and that kind of thing. But design is open-ended, and so what we need is tools or a systematic process to allow us to deal with an open-ended problem in a very systematic and calculated way, such that the solution we get isn't just, 50 and 20 or whatever we've picked out of the sky. It's actually meaningful and we can justify why we've chosen that. All right? Because you're going to need to justify it to, if you're selling it to someone, they need to understand it, or if you've got an employer or a boss or a manager or whatever that's asking you to do something, you need to be able to justify that. So we need these systematic approaches to engineering design, and the standard one that we actually use is the 5-step design process. Has anyone seen this before? Yeah, a couple of people? So it's pretty straightforward, 5 steps. First one's define the problem, work out what we're solving. Next, gather important information, so that's kind of the research phase. There's no point reinventing the wheel, and we'll talk about that. Generate multiple solutions, so this is your brainstorming, what can we do kind of section. Analyze and select the best solution, and then implement and test the solution. And you see my little arrows there that indicate that it's a cyclic process. That's because design is a cyclic process, funnily enough. Cool. So what we're going to do is come up with a bunch of solutions. We're going to try them out, and if they're crap, we throw them away. And if they're almost there, then you go back and improve them a little bit, and you try them again, and you keep doing that. Ideally as few times as you can, because your design in the first place will be good. But this is the process that we follow to design things. And this is so we don't miss things. This is so we get a solution that actually solves what we need to do. And today and into tomorrow's tutorial, we're going to talk about number 1, define the problem. Because define the problem is probably the one that gets overlooked the most easily. And it's probably the most important one. Because if I told you all right now, go and design me a bridge, hands up whose first thought is, all right, am I going to use a triangular structure or a suspension structure, or how am I actually going to build it? Yeah? Some of you are going straight to design, which is fine. That's the engineer, the creative in us wants to go straight to that. But what we need to do first as engineers is resist that and work out what is the actual problem we're trying to solve. Because I can't come up whether I want a beam structure or a suspension structure or some other form of bridge until I work out what the bridge actually has to do, and then I can, follow through. It's a systematic process, and you've got to go through the motions at the right time. No good doing this at the end. We've got to do this right at the beginning.
Just one quick question.
Yeah.
When you're saying about what does this bridge have to do, doesn't the bridge just connect one point to the other?
Which point to what point? What winds? What vehicles? Is it a person bridge? Is it a car bridge? Is it a bridge like in our example where I'm just going to load it up with weight plates and try to make it break? What other conditions? What's it allowed to be made out of? I'll talk about all of that. So that's why we're going through number 1 now, because I'm going to explain exactly what the methods are to achieve this particular definition. So effectively, at number 1, someone's come to you with a problem, and tomorrow morning I'll give you the outline for your project. So that's me coming to you. I'm the client or the boss or the manager or whatever you want to think of. But effectively, the source will present the problem to you. And generally speaking, that'll be pretty airy-fairy or not a lot of information on it. So that source can be a client or a company or a manager. It might be a client brief. So you might get a document that says, we want to solve this problem, or this bit of equipment broke and we need to unbreak it, or something very vague and very high level. So here's a problem, fix it. All right? And oftentimes it'll be pretty light on specifics. All right? And so what your job in the very first instance, in those first meetings that you have with clients, be it me or otherwise, is actually start to dig down on what those specifics are. Because a client will have a very specific idea of what they want, but they might not communicate that to you. So if you go, right, good, I've got it, got my paragraph, off I go, and start designing stuff, spend 6 months and come back to them, and it's completely different to what they had in their head, it doesn't matter how good your solution is, because already you haven't won them over. All right? If someone has an idea in their head, it takes 100 times the convincing to get them to change that than to just work with that and go in the direction that they think it should go. All right? So what you need to do in the first instance is really clarify clarify what that problem is, okay? And so you're talking to your clients, you're talking to people. This is where people skills, group skills come into it. All right? Now, I've got a couple of examples here and we're going to discuss it. These are just examples for us to discuss how we might clarify, where the information might come from and what sort of information we might need to get from that client to actually define our problem. So the example one is, I want to design a clean water supply for a third world country. All right. Who might actually come to you with that type of problem?
Usually volunteer organisation.
Volunteer organisation? Yeah, government of some other country or your own government. What else? A World Health Organisation, yeah, the World Health Organisation. Anyone else? Yeah, so there's lots of different companies that might come to you. You might work for a company that does this kind of stuff. What sort of questions would we need to ask? Sorry, what type of materials? Yeah, so what should it be made out of potentially? Which country? That's a helpful one. Budget, yeah, good. Budget? Where's it going to get put? Yep. Sorry, I can't hear. Oh, hang on, where'd that come from? Where the water come from? Yeah, up the back there. How many people is for? Yeah, so what sort of throughput do you need? Up the back? Climate, yeah, that's a good one. Over here? No? Yeah, bore water, so what type of water? What type of contaminants are in the water is probably helpful.
Surrounding environments.
Yeah, so what sort of environment around this can impact it? So there's lots of different...
Local or individualized, is it for a local community or is it for individual?
Yeah, absolutely. So is it just a personal one-person water supply or is it to a larger supply for the people? So there's lots of different questions that you'd need to actually clarify. If someone comes to you and says, I want a water supply for this village, how big's the village? How many people? How far away is it? What sort of filter can it be? How do we maintain it? How do we do all of this? So there's lots and lots of questions that we're going to be asking. What about this one? Has anyone seen this one? This type of thing? This is called a tippler. So if you can't really make it out, that is a rail carriage full of coal. All right? That thing's pretty heavy. So the question that your client might come to you with is, I've got a rail carriage, it's full of coal, I want it to not be full of coal anymore. All right? And how do you solve that problem? The reason that you actually design this crazy big apparatus to tip it upside down is that coal's pretty sticky. And so has anyone seen rail carriages with like the hoppers underneath them and trapdoors that drop out? Yeah, so that's actually a pretty big problem with a lot of bulk materials because they pull it up over a big collection or conveyor belt or something and they open these out and some of the material falls out and some of the material actually arches and just stays there. Think of like wet sand in a Coke bottle, right? This stuff's pretty sticky. And one solution, and this is in your when you come up with multiple solutions sort of phase, but one solution to this is that when they have that problem, they actually have a couple of giant big jackhammers come up, connect to the carriage and shake the bejesus out of it. And anyone that's seen some of the different loading stuff at the port will actually see some examples of that, all right? And just vibrate the bejesus out of it and all the stuff falls out, all right? But obviously that's going to have massive impacts on the long life of your carriages and all the rest of it. So there's alternates, and one of the alternates, they use it at the port here. Wilmar use it with all of their sugarcane carriages and various other, this is very common that you have a tippler, giant big many 100-ton carriage goes onto it, you roll it upside down, empty it, and you put it back on the track and on it goes, all right? So this is what seems like a pretty weird solution or a very excessive solution, but it's probably the least impact on the carriages, and if you design it right, it'll last for decades and you'll be right. But again, you've got a customer who might have come to you and said, I've got coal, I want to get it out of my carriages, and now you need to work out what sort of implications, what's the sort of question that you might ask regarding this? Yeah, so how big are the carriages, how much coal, what's your throughput, what else? Budget, how much budget have you got? Sorry? Where's it going? Yeah. How much room have you got to put this? Can we fit a tippler, or can we only deal with a very small collection? Yeah, so how many people are there? So in regards to how many people are you happy for operating it, certainly, and various other implications?
How many times do you want to use the carriage?
Yeah. So what's a life of a carriage? And obviously we want to use it more than once.
How do you already empty it? What's the problem with it?
Yeah, hey, there's a good one. All right, what's the problem with current situation or methods? If you don't understand that, you'll probably redesign what they've already got and still have the problems that they've already got.
Would gradient come into account?
Gradient, so what, how far you tip it?
No, like the truck itself, like if the ground flat.
Yeah, true. So is the area flat that you've got to actually put this? Can we dig a giant big hole and actually build this equipment there, or do you not have the space? Yeah. So lots of questions like that you need to start digging down on the client. Last one, airbags. Who's likely to bring a problem of airbags to you? Car manufacturer? Yep. It could be, the actual car manufacturer. It could be a car manufacturer that has airbags in place and has some big problem with them. Everyone heard of cars? A few different car makers lately having problems with their airbags exploding or not exploding, either way. And recalls and things like that. So there's engineers now working out what the hell's going on with these airbags that aren't working or aren't deploying or are breaking people's necks when they do deploy. So there's lots of different areas where you could get this. What sort of questions would you need to ask a client? All right, so the client's come to you and said, I want you to design a better airbag system for my car. How big's your car? Define better? Yeah, exactly. That's exactly right. Because they'll come to you and say better, and you need to understand what better is relative to.
Storage space for the airbag?
Yep, what have you got to fit it? Yeah, so where's the actual, the car positioning for the occupant? So where's the steering wheel? Where are the side impact structures? Where's the occupant going to be relative to it? How fast do the airbags release? Yep. And there's also a lot of standards and safety standards and things around this, so they need to tick all of those boxes as well. And whether they actually have a standard deployment or whether you have to come up with it. So there's lots of different, one last one. Yeah, what sort of airbag is it? Is it the front one in the steering wheel, or is it the side ones or the curtain ones, or are they all up for redesign? So there's lots of different questions to define this. Okay? And a lot of that comes through the clarification of specifics. And we need to clarify exactly what's being designed and what your job is and what they expect of your job. So we've been talking about it and answering some of these questions here, but understand the systems, its functions, its needs. What's it need to do? What's the actual broader system? Where does this fit? Establish constraints and objectives. So, how much money have we got? How much space have we got? How many people have we got to build it? What's our time frame? Consultation with client and stakeholders. So your client might be the one giving you this information, but are they the only person we care about? Who might be a stakeholder for, let's say, the third world water supply? I think I might even have that. So who's a stakeholder for a third world water supply? People using the water? Anyone else?
The government of the country you're going into.
Yep, government, and it doesn't matter whether the government's the one employing you or whether the government's just there, but the government certainly will have stakes involved. They might be paying a different aid organisation to do the water, and they might be really pissed off at you coming in and redesigning water supplies when they've got other things in the works. So we need to talk to them and make sure they're across it. Anyone else? Yeah, absolutely. So just the people living there aren't the only stakeholder. You've probably got animals and, environment as well, and you can't talk to the animals, but you can certainly talk to experts that understand the ecosystem and actually treat them as a stakeholder sort of by proxy. So that's a good one. Anything else? No, that's pretty good. So, and potentially also whoever's paying for it. So whoever's financing something is always a stakeholder, and they've got a reason to be paying for it. So whether that's, an aid organisation or otherwise. Who are the stakeholders in this one? Mining company? Yeah, so whoever's actually paying for this.
Railway company?
Yeah, railway company, because the mine might not own the carriages, certainly. Sorry? Yeah, industries that rely on the mining. Everyone's seen the couple of train derailments that we've had sort of between Mount Isa and Townsville? You've seen the implication that that has. That's not just, you can't get your material out of the mine, although that's a massive thing. But now you've got all the people that are working at the ports and things like that, and they're not getting the stuff to do their job, so they have, implications. There's many wider scale stakeholders than just a particular company that's doing something. Anyone else? Yeah, cultural significance around the area, absolutely. You always need to take that into consideration. Local government, yep. What about, how noisy do you reckon unloading that thing would be? Yeah? So are we right behind a residential housing development where a giant rail carriage full of coal emptying every 30 seconds is going to impact? That's a big one, because I can guarantee you that will shut you down. It's shutting pubs down all over the country because, people are moving in next to live music venues. There's lots of different sound implications, and I can guarantee you, even if it's a tiny little bang, if that tiny little bang repeats, that will drive you insane in your house. So it doesn't need to be close, but it just needs to make enough of a noise regularly to really drive someone insane. Okay, last one. Stakeholders? Drivers, who else? Passengers, who else? Queensland Transport, that's a good one. Who else? Insurance companies, absolutely. Obviously the car manufacturer, yeah? Children, yep. Anyone else? Yeah, there's probably a few other people. Emergency services personnel. So if these things deploy and you're now the AMBO or the firey trying to get the person out of the car, what do they understand about these things? Or, even more important, these things haven't deployed and you're now the firey trying to cut someone out and then it explodes on you while you're trying to cut someone out? Yeah. So that's why we mean stakeholders in a very broad sense. Not just the person paying you, not just the person using it. What is every possible use case or possible impact that a product might have? All right? And in terms of emergency deployment stuff, then you definitely have to consider the emergency services personnel. All right. So once we've clarified things, we've talked to our clients, we've talked to other people, we need to produce a problem statement including criteria for success, and then you'll generally hand that back to the client and say, this is what we understand of the problem. Is this your understanding of the problem? Because if it is, that's what we're going to go forward with. And you might actually iterate on that a couple of times, because they might say, no, you've got it completely wrong. This is actually what we want. All right, so even after consultation, once you put one of these statements together, it might get rejected. And I think I've got 1 or 2 slides left, guys, so we're going to go straight to an activity after this. But producing that problem statement is really the first stage of design. This is what we do. The other part is consultation and understanding the problem just for yourself, but this is the formal document that you fill out, the first page or the first chapter of a design report. You produce this problem statement that explains your understanding of the problem and documents every single place or bit of information that you've found before you've even thought about a solution. Okay? This has nothing to do with the fact that we're going to have a tippler or we're going to have trapdoors in our rail carriage. This is purely just understanding what the rail carriage has to do. All right? And there's a few categories. One is performance, obviously. So function, appearance, reliability, loading, environment, cost, quality, weight, noise, dimensions, standards, etc. So this thing obviously has to perform. It has to function and do some sort of function, and you have to explain what that function is formally in this document. Operation. So operation is different to function because operation means someone actually has to use the thing. So it might do its job, but if it's impossible to actually use, then that's a problem too. So who's got to use it? Who's got to install it? Who's got to maintain it? The number of times I hear how mechanics hate mechanical engineers. You introduce yourself and, oh, what do you do? Oh, I'm a mechanical engineering lecturer. Oh, fucking mechanical engineers. Because they'll design these engines to be put into a car, but then when it comes to do something simple like change a transmission or something, it's an absolute nightmare. They've got to drop 18 components just to get one out of the car because the maintenance wasn't considered in the design process. So you've got to both think through how is it going to be built, how is it going to be used, and how is it going to be removed in the case of breaking or needing maintenance, and who's going to be able to do that, and how much of a pain in the neck is that. All right? Particularly for things that have long lives, and that includes all of the sorts of machinery you'll find in a mine or a refinery, and all of the type of machinery you'd use in everyday life, cars, trucks, etc. All of that stuff has a very long service life, and so maintenance is very important. And safety. So while you're operating, you need to operate safely. Manufacturing requirements. How are we going to build it? What are we going to build it out of? Quality, etc., etc. How much energy is that going to take? How much impact is that going to take on the environment? And, you know, all of those type of considerations. Disposal requirements. What would be the disposal requirement on one of those filters? Have they got fancy recycling plants that can decontaminate chemicals? Third world country. What's most likely going to happen with a filter when it breaks in a third world country? It's just going to toss it there and then. They might have some landfill, or it might just be a hole that they dig on the spot, or they might have something more sophisticated than that, but fundamentally the expectation is in a developing area, in a village that doesn't have, you know, garbage trucks and so forth, it'll just go into landfill, it'll go into some sort of a pit. All right? So if you make something out of chemicals that are then going to leach into the environment and destroy everything, obviously that's a really bad design. You need something that can just be tossed and degrade. And accepted standards, everything that we do is dictated to by standards, be it Australian standards, be it safety standards, be it environmental impact study, blah, 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 yeah? So it's your job right at the very beginning to work out which one of those apply to your particular design and make sure that you adhere to them at every single step of the process. Okay? So you need to go out and actively seek those, find out what they are, and then adhere to them. All right. So that's all the slides I have on this. What we're now going to do is an exercise, and I have what is called a PDS, which is a product design specification. There is a little chapter from a textbook just explaining how to fill one of these out. I've printed 80 of them, which is 1 between 2. So in groups of 2, you can grab one of these and then I'll explain what the task is, okay? It's also on LearnJCU, so if you've got a device, feel free to get that out and pull it up. But otherwise, share 1 between 2. This will be your job for the tutorial tomorrow as well, guys.
Do we have a textbook?
Sorry?
We don't have a textbook.
There's no textbook, no.
Yeah, there's no textbook.
Yeah, I just give you these sort of things. All right, pass them around. Here we go. Pass them around. All right, so I'm very serious. 1 between 2, guys, otherwise there won't be enough. Could have printed out 150 of them, but that was going to be a lot more trees than 80 of them. There we go, and they're making their way around. Yeah.
We have workshop on today.
Tonight, yeah. Yeah, workshops are on today, guys, if anyone's not done them yet. Okay. Here we go. Pass those ones around. Here we go, guys. We got spare ones? Oops. Great, thank you. You guys need one? There we go. All right, pass that. How are we going at the front there? You guys have one? Cool. All right, that'll get to you. Pass this at the back. Here we go, guys. Pass this. Oh, you got some, got some, got some. Cool. One there. How many more over there? Okay, can you pass those ones over there and work it back? All right, we got spares anywhere? Are there? Yeah, good. Spares? No, one each, guys. One between two. You guys both got one? Yep, cool. Here, thanks. All right, who's missing one? Cool. All right, we got some spares. Great. All right, so the spares there, spares there. Cool. Here, pass some of those spares around and some people can have more. All right, if everyone can see one, any spares, just pass them around. Oh, have you guys got everyone under control? Cool. All right. So this is the product design specification. I might even pull it up on the slides here. This is effectively the formal way of documenting what I want, this problem definition. All right. You are going to produce one of these for the bridge design process tomorrow in the tutorial. So I suggest you read it in detail tonight. What I suggest now is we'll skim read and I'll tell you what the task is. But the most important part, it's got a bit of a definition about what each of the sections is. Here, these are the different categories for what we're going to be looking at a product. So on page 20, performance requirements, manufacturing requirements, accepted standards, disposal and operation requirements. So those are the different categories that I talked about, and there's some subsections there, sections that actually explain each of those categories and the subsets of those that you might need to consider in this document. So you can read those very briefly today and then hopefully in a little bit more detail tonight such that you're really well across them by the tutorial tomorrow. The other thing that I'll point out is on page 27, this is an example of how I want you to lay one of these out. Alright, so that's the starting point. Product design specification for something. Alright, so for tomorrow's going to be the bridge. Today I think we're going to do a can opener or something. There's space for related specifications, issuing authority and contents. If it's very, very long you might need a contents, but we don't need any of those sections in this particular one. What I do want is a foreword. Who's written one of them before? Anyone understand what that is? It's basically an abstract, a summary, a general summary of what's going on. In this particular example, this is for designing of a suspension seat for an excavator or something like that. The foreword, the photograph in figure 2.8 shows an excavator loaded, historically prior to blah blah blah, and it gives you a little bit of the background and a little bit about what's actually required. I expect you to write one of those for your bridge tomorrow, and you can write a bit of something like that for today. It just takes a couple of sentences. It introduces exactly what this document is. It's good writing, and you need to get across how to actually write one of these. Oh, what you do for your bridge tomorrow, that will constitute the first chapter of the design report that you're required to submit. Okay? You'll have to write a bit of bridging sentences and we'll have a lecture on how to do that. But each one of these tutorials, you'll have one of these documents to fill out. That document then constitutes a chapter in the final design report. So I'm going to walk you through writing a design report this semester. And this is the first chapter. This will be the introduction. Okay? So do it properly because then you won't have to redo it when you're submitting your design report. Okay? Introduction. So introduction's very brief in this particular document, but the objectives are to design a suspension mechanism for the operator's seat, to design the mechanism in such a way, blah, blah, blah. Okay? And then scope. What is the scope of the design? In this particular case, all machines, whether with a fully enclosed cab or simple canopy, are to be provided with such a suspension mechanism. That's for the particular seat suspension example. So that's kind of the introduction front end. You need those sections. And then you have definitions, if there are any, and then the 5 categories. All right, so performance requirements, manufacturer requirements, acceptance standards, disposal and operation requirements. And you need to think through each of those things and write dot point or comments on each of those, how they specifically apply to your project. All right? And then once you've addressed all of those, hopefully you will have thought about enough to actually define the problem properly. And under each of those, remember that, for example, under manufacturing requirements, you think about the processes, the materials, the assembly, the packing, the quality, and the delivery date. All right, so those are the particular subsets that they've suggested for that. If you consider over each of those and anything else you can think of and comment on those in that section, then that will be sufficient for that section. Make sure you have all 5 of those sections. Even if, well, there's probably, for what you do for the bridge, we might not have acceptance standards. There's probably no AS standard for toy bridges. But even consider if any standards related to actual, civil infrastructure type projects, whether they apply. And even you can mention it and then say that it doesn't apply to this particular application. Okay, so that's fine, so long as you demonstrate that you've thought about it. For all the rest of them, I would think that they would apply to your particular bridge. Okay, but today, just so you get a little bit of a feeling for how this works, in your groups of 2 or 3, depending on what you want to do, what you're going to do today is write out a quick one. We're going to spend about 20 minutes on this, then we're going to share, and then we're going to be done for the day. In the exercises on the last page, number 3. A market opportunity exists for a can opener which is operated by a disabled person with only one hand. Think about that, what that means. Can opener for a person with one hand. Ordinarily your can opener, you're operating like this. It's probably a real pain in the neck to have one hand and try to use a can opener. The device is to open a can in such a manner that contents are not spilt or contaminated. The contents can be easily removed and no dangerous or jagged edges are left exposed. Write a specification for the device. Okay, so what you're going to do now in your group of 2 or 3 is do all of the things that I just said. So you want your forward, you want your introduction, you want your scope, and then you want to consider the 5 different performance categorizations for that particular one. Feel free to discuss it, feel free to ask questions of me, start thinking about how to PDS this product. So in the interest of calling it a day, let's have a quick chat about this and then we can nick off. So obviously you're going to do this again tomorrow for your tutorial. I suggest you read this document tonight in full if you can, or at least anything that you didn't manage to cover just now, such that you can hit the ground running tomorrow and you spend your hour and have it mostly finished by then. I haven't decided whether I'll make it due tomorrow or not. I think for the most part you're going to use it and put it in your design report anyway, so tomorrow will be our opportunity for you to get it signed off and talk to myself and Brent and meet Brent and work out what's involved. I'll probably take a roll at tomorrow's tutorial and call that 0.5%, so we'll just do that. Alright, so let's assume that you're able to write a forward, an introduction and a scope, because that stuff's just the righty stuff. For the most part that forward should really involve the general background. So general, something like can openers generally operated with 2 hands. This poses a problem for people differently able with only one, and so there exists a need to create a can opener for such people that can be operated with one hand, be it electrical or mechanical or whatever. Bloody hell. So something like that, and then your introduction is going to be very specific. I've already talked about scope, so in this context scope's pretty easy, maybe just that it's mass produced, not a custom job, and then you're done for that. Alright, so performance requirements, and I might go back to this figure so I can cycle through each of these. Alright, what's our function? Can opener, one hand, can be mechanical, electrical, doesn't really matter. Alright, what about appearance? We talked a little bit about these, so. Sleek, what's the major impact of appearance? Sorry? Over here, yeah? Yeah, wanting to buy it. So fundamentally, if it looks like shit, no one's going to buy the thing. So that's, you might say in that particular section, the major characteristic for appearance is that it is attractive for purchase. And whatever that means, be it, different eras. So A product now will look very different to a product 20 years ago, so you want to adhere to the sort of cultural norms for that product, or go a little bit further than that if you want to be, Apple or someone like that, something sleek and technology looking. Environment, reliability. So how long is this thing got to last? 10 years maybe? How long a warranty are you going to put on it? 3 years? Yeah, maybe. If you got really good design and you're making it in Germany, maybe 3 years. If you're making this as cheaply as possible, and let me recommend to you that you make this as cheaply as possible, 1 year is probably good. All right, so aim for 10 years, but if someone treats it poorly, then maybe after 1 or 2 it breaks. It's not the end of the world. And if it's only, if it's $200, it better not break after a year. But if it's $20, $30, then maybe someone can cope with buying a new one. That's not a problem. But all of that, that's the conversation you have. That's all right, we expect it to last for 10 years. It is a product that will be sold cheaply, so a 1 year warranty will be appropriate. If it breaks after that period, so long as it's only a small proportion of them, then that's appropriate. Yeah, something like that. Environments. So what sort of environment? We talked about that. Ex-works cost. Did you guys read the definition for that? I had to look it up again. Ex-works basically means how much is someone willing to pay for it. Doesn't matter if you invented a NASA can opener and it costs $1,000, someone's not going to pay $1,000 for your can opener. So at some point your company's losing $950. How much is someone willing to pay for it? Because then that dictates how much are you able to design into it. All right, so if someone's paying this much, then it has to cost this much for manufacture, because they've got to mark it up, and then the wholesaler's got to mark it up, and then someone else has got to mark it up, and you've got to make a profit somewhere along the line as well. So somewhere in the order of 1% of the final price, if it's a product, that's how much it's got to cost to make. All right, and that dictates how high-tech it can be. All right, maybe not 1%, there's business people who will tell you the actual percentage, but it's very, very small. It's not like half of what you can sell it for you can make it for. It is a tiny amount of what you can sell it for. Ergonomics, has to adhere to the hand, yeah. We'll get through these quickly. Quality, weight, noise. Should it make a heap of noise? No. Should it be heavy? No. Yeah, one hand. So you've got to operate it with one hand. You're already talking about someone that's differently able. Maybe they got a super strong hand because they favour it. Maybe they've got a weak hand because they don't. Whatever. So it's got to be light and easy to use. All right, what was next? Let's talk about operation requirements. Did anyone get to that? Installation? Any installation required? Hopefully not unless it's like an electronic device, but let's say not. Like something that builds in. Use? Should be able to be used by children? Yep. What else? Who else is using this? Either hand, good one. So left hand or right hand. So which hand have they lost? Just because everyone's right-handed doesn't mean that everyone loses their left hand. You need to be able to use it both hands. And if you're going to have a left-handed, one-handed can opener, have you got a big market for that? Probably not. So it's got to be very ambidextrous, yeah? Maintenance. Are we maintaining this? How many people have taken their can opener to a mechanic recently? Yeah, over here? All right, good. Very, very, very caring about his can opener. That's good. I like someone that cares about their stuff, but fundamentally most people will not take a can opener. So effectively the way it's built is the way it's going to be, plus or minus a heap of dirty food and shit all gunked into it. All right? Safety. What is this fundamentally? It's a rotating blade. So safety is going to be quite important. You need to shield it from that. Yeah, absolutely. So that was part of the criteria as well, that it can't make a sharp edge on the can either. So that's got to be safety. And not cut themselves. Yeah, absolutely. So, yeah, well, if it's either way, electric or mechanical, you shouldn't be able to cut yourself, and it should be relatively fail-safe. Remember what I said about fail-safe with the oil thing? Fail-safe is if someone's actually trying to cut their finger off with it, they'll probably succeed. But outside of that, you shouldn't be able to get something caught in it and sucked in. All right? So that's operation requirements. Everyone should have a couple of things for that. Manufacturer requirements. So how are we going to manufacture these? China? Probably. Well, it's not a joke. Everything gets manufactured in China because they have massive manufacturing plants and they can do it crazy cheaply over there because they do it so well. It's moving towards other countries because China's I don't think you'd call it westernising, but China's modernising, and so it's becoming more and more expensive to do stuff in China. So you're going to other countries around there, around Southeast Asia and things. But so process is probably going to be some sort of mass produced in somewhere like China or otherwise. Materials, what do we build them out of? Plastic, some parts. Rotating parts out of? Metal, what sort of metal? Aluminium, maybe. Aluminium bends pretty bad. What else? Steel? Raw steel? Stainless? Yeah. So you probably, if you're making this for 10 years and it's going in dishwashers, you want everything stainless steel that isn't plastic. And you can even talk about the quality of stainless steel because there's different prices for different types of stainless steel. What about assembly? So there is going to be assembly of this thing. Hopefully the user doesn't have to assemble it. So assembly should be, again, production line or something like that, yeah? Yeah? Packing. Cardboard box. So are you going to buy this thing in a cardboard box in the shop or is it going to be hanging on a shelf? If it's a hand one, it's probably going to be hanging on a shelf with about 100 others, but it has to get there. So when you're talking about packing, you're saying at storefront, product will be loose, but to get to storefront, need to pack in box safely with probably 20 others or 30 others or whatever. So the major packing involved is if you're putting them all in a box together, they can't destroy each other, so you've got to think about how they pack around each other. Yeah, shipping. How do you get them from A to B? If you're talking about cans of Coke, you talk about the can of Coke in a six-pack, in a box, on a pallet, in a truck. Like there's packing all the way along there and you need to think about all of those things. And the can itself is packaging. So, all of those aspects of packing are very important and they all deal with your manufacture. Quantity, we said relatively high, probably not tens of millions, but certainly ideally in the thousands. I don't know how many people with one hand need can openers. It's probably not a huge amount, but there's a market for it because that's the people that are paying you. Delivery date, we haven't specified, so you just say TBA or something like that. Acceptance standards. Anyone come up with any standards or think about what sorts of standards might be required? Yeah, so there's mechanical bits, so what we'd have to do is do a search on some sort of mechanical standards. What else? Food safety, that's a good one. I didn't think of that one. Food safety, there'd definitely be standards around. What sort of materials can be exposed to food? No good having beautiful food standard stainless steel and then impregnating that with heaps of grease. Yeah, so that your rotating parts stay rotating and bearings and things like that because grease is obviously not going to deal well with the food. So already at your rotating parts you can't have grease on them, so you need, food appropriate materials. So that's a good one. What about if it's electrical? There'd be some sort of electrical appliance standard or something like that. You guys would have to search. So in this context, just write a couple of dot points, but you would then go and do the full search of what standards exist because that will restrain where your design lives. Inspection and testing. I had a discussion up the back about inspection and testing. What sort of inspection and testing would we be happy with this particular one? Yeah, so when you first design it, you'll have actual case studies and people trying it, but when you're actually manufacturing this, would you try 1 out of every 50, 1 out of every 100, 1 out of every 10, maybe? It depends on how many you're producing and how costly it will be for someone to take it out and test it, yeah? If you're making millions of them, then you might test 1 in 10,000 or something like that and make sure they're working. If you've got an electronic production line, that might be as simple as some sort of a scan as they go past and make sure they're, you can tell a lot just by visual inspection and write some sort of a scanning software that identifies what is and isn't a fault. All right? So again, computer system, electrical engineers, image processing, all of that kind of stuff. If we're doing really large scale stuff, maybe we go down that road and then someone doesn't have to physically pull one out. But that's the sort of conversation you have there. Patents. You would do a patent search immediately on any one-handed can openers, because you might spend 6 months inventing the best one-handed can opener and then get the heck sued out of you because someone already came up with it. Things get designed the same independently. All right, so just because you haven't seen someone's work doesn't mean you can't design it the same way as them, and if they have a patent, they can sue you, and it doesn't matter that you've never seen theirs ever. If it's the same, they sue you, they win.
Good question. I've seen some products that says patent pending.
So if you've applied for a patent, sometimes it actually takes a long time for a patent to get approved. Applying for a patent is as good as a patent, so much as it protects you. So once you've applied for it, you've proven that you've designed it, and that is a legal document and it protects you. Once the patent's approved, there's more protections and you can sell it. I think there's restrictions on how portable your patent is when it's still applied for, because you can't sell something that then might get denied down the line. But fundamentally, patent applied for and patent is the same in the context of you'll still get just as sued for copying them. Cool. And last one, disposal. How are we disposing this thing? In your wheelie bin, probably. Yeah? That's where it's going. Are there any standards around that? Probably. You can't put batteries in a wheelie bin. You can't put, various types of chemicals in your wheelie bin. So you'd have to make sure all of the restrictions on what you can and can't landfill aren't in your product. Legislation, same sort of thing. What's your company policy? Does the company policy have, company have a policy on that? Hazards, is it hazardous to the environment? What else around disposal? What's one of the most important things in today's engineering? Recyclable. How sustainable is your product? Because landfill is a very different equation to completely recyclable, all right? And so what you want is something that can be recycled. And fundamentally, if it's made out of plastics and stainless, you should be able to stick it in your recycling bin rather than your wheelie bin. All right? But if it's got, materials that can't be recycled, then that's a problem, and that's a worse impact on the environment, and that's a worse outcome for you in general as a design engineer. Any other comments on that? No? Cool. So treat that as an exercise. You guys should be now a little bit familiar with the process. Please finish familiarising yourself with the process, and then we will apply that once you have your project tomorrow on the bridge. Cool? All right. I'll see you all then.